Hello, my name is Delisle Paulette. I'm a PhD student at the University of Calgary, and my colleagues and I performed a study looking at running on the moon and how people adapt their gait in reduced gravity. I'll just start off with a video of a normal human running. Now, we can describe this gait in the video as normal because every healthy human runs more or less like this. Isn't it interesting that gait is so consistent when so much coordination is happening? But it's true, gaits are so consistent that we often forget the alternatives. These were humorously exemplified in the video game Quap, where players had to activate thighs and calves separately. Now, this is rather difficult, so they came up with some unique ways of getting from A to B. Now, given so many alternatives, why is it that normal gaits are normal at all? A simple explanation is that normal is normal because it is less costly. Here's what I call a cost surface. Each of these unique gaits has an associated metabolic cost. The idea is that normal gaits are at a minimum on this surface. But what's on the x-axis? Clearly, there's not one variable that can distinguish these gaits, but it's likely a combination of frequency, step length, forces, torques, and so on. So this isn't just a one-dimensional surface, but a multi-dimensional surface. You may think that there are just too many dimensions for human to be able to explore and optimize, at least in a realistic time frame. But today I propose that every day we humans navigate these complex cost surfaces to find energetically optimal gaits, and that we are so good at it that even when subject to circumstances we've never experienced, we can find the best solutions. Now, how do we test this idea? Well, we can introduce people to novel circumstances that change the shape of this cost surface and see if people will adapt their gait accordingly. And one such novel circumstance is being on another planet. Of course, it's pretty expensive right now to send someone to Mars. Hollywood can get around this by just imagining what it's like. So take, for example, the movie John Carter. Now, putting aside that this fellow is not suffocating or freezing to death on Mars, let's see how the writers thought he would run in his first experience in reduced gravity. So here he goes, and he's jumping really high into the air. Now, this is a common assumption about running in low gravity. If you can jump high and maximize your flight phase, why not do so? But we want to test this ourselves in the lab. This complex mechanism provides a constant upward force to counteract the effect of gravity. Effectively, it reduces a person's weight so they feel like they're on a different planet, and it can simulate gravity as small as the moon's. So here's a video of a person running in normal gravity. At about a jogging pace, the video is slowed down 4 times, and they take these large vertical undulations. But when they're subject to reduced gravity, so this is about moon's gravity, they actually flatten their gait and take these really low arcs. So this is a pretty unintuitive result, and it begs the question, why isn't running on the moon bouncier? From an energetics perspective, we thought the same thing as the writers of John Carter. In running, the flight phase is virtually free of energetic cost. You primarily lose energy during the touchdown phase when your body effectively collides with the ground. But there's an issue if you want to maximize your airtime. To do so, you need to maximize your vertical takeoff speed, which means you're going to come down at a very large speed and lose a lot of energy to the ground. This is why, incidentally, when you skip a stone, you need to approach with a shallow angle, minimizing the vertical speed. The rock loses less energy to the water and can keep on going. So maybe the same strategy works for running. We just need to reduce the takeoff speed. And we can do this by taking shorter steps. And if we take even more steps, it's even better. Now, every step has a very low vertical takeoff speed and therefore very low energy. This means we need to take steps really, really quickly, and the fast leg swing is costly. So there's a trade-off between the cost of collisions and the cost of leg swing. And how do we calculate this trade-off? So we used a really simple idea. Let's suppose that a person is just a point mass. Right before they land, they have this vertical velocity v and a horizontal velocity u. As soon as they land, they lose all that vertical speed, but the horizontal speed is untouched. This means they have to add back the vertical speed with energy 1/2 mv squared. This tells us that energy should increase with v squared. But remember, there's also a cost for step frequency. We'll say that this additional cost increases with frequency squared. The reason for this is that the faster you swing your legs, the more work you have to do. It just so happens that the swing work is proportional to frequency squared. By the way, we don't know what this A value is, but it's probably related to the morphology of your leg. For example, a longer and more massive leg is harder to swing. Now, what is this frequency in terms of vertical velocity? Well, again, let's suppose you start with a vertical velocity v. That means you're going to enter the flight phase and take on this parabolic arc. And halfway through the flight phase, the velocity will just be 0. The time it takes to reduce your velocity from v to 0 is just the initial speed divided by the rate of deceleration, which is g. So frequency is the reciprocal of that, or g over v, which you can replace with f down here. Now we have a relationship between total energy, vertical takeoff speed, and gravity. In effect, we have a cost surface. Of course, this is just a cartoon. What exactly does it look like? Well, since we have an exact formula, we can plot it. What we have here is energetic cost as a function of vertical takeoff velocity. The black line is the collisional cost, and this increases with velocity squared. The leg swing cost takes on an inverse relationship with velocity squared. And the total cost is a balance of these two effects and has this bowl shape with a unique optimum. Now this is at normal gravity. Well, what happens if we reduce gravity by half? Well, now the collisional cost hasn't actually changed. The reason for this is that if you take off at 2 meters per second, you're just going to land at 2 meters per second. It doesn't matter how long that takes. So the energy you lose, and therefore the energy you have to give back, doesn't change no matter what the level of gravity is. But the frequency-based cost does change. Lower levels of gravity don't accelerate your mass as quickly downwards, which means you can get farther with a lower vertical takeoff velocity. So in lower gravity, the frequency-based cost shifts to the left, and this means that the optimal value also shifts to the left. And as we keep decreasing the gravitational level, that optimal value of the vertical takeoff velocity keeps decreasing as well. At the lowest level of gravity, so this is about Moon's gravity, the vertical takeoff speed is less than half of what it was before. So what we have now is a whole suite of predictions of how people will change the vertical takeoff speed with gravity. In particular, we predict that the takeoff speed should be proportional to the square root of gravitational acceleration. But we need to actually test this. So we asked 10 subjects to come in and run at 2 meters per second at around these levels of gravity shown with the yellow stars. And this is what we found. The trend line predicts their behavior beautifully. It's not a subtle effect either. At the lowest level of gravity, subjects are using less than half the takeoff speed they used at normal gravity. What's most remarkable to me is that subjects adapted very quickly. These trials were only 2 minutes long, so within 2 minutes they've adapted even if they've never experienced reduced gravity before. So what we learned from this whole experience is that low gravity running is actually less bouncy than running at normal gravity. Humans lower their takeoff speed in order to balance swing and collisional costs, and these are governed by very simple principles. The idea of the cost surface was central to predicting behavior, and it's remarkable to me that people are very good at adapting to these cost surfaces.